Okay, so today we are going to discuss volumetric representations and deep implicit models and neural networks to represent and implement this kind of 3D representations using neural networks. And as I mentioned, these two types of representations, volumetric representations and deep implicit models, they are representations that are extrinsic, that represent 3D objects in the ambient space as a functions of the ambient space. So we are going to start with volumetric representations that are discrete representations in the ambient space and has many connections with what we have seen so far in the course for images. And so as an outlook, what we are going to see in this area is that these 3D representations, they are natural extensions of what we have seen so far for images, and we extend this for images with geometric information, and then for full geometric information. So we go from 2D that are images, and then 2.5D that's images with additional geometric information like depth or normals, and then we end with full 3D information. And these are natural extensions. One important thing that we are going to see is that these representations are very regular. In the same way as an image is a 2D grid, and you have information as a regular sample locations, we can extend this for each point in the image, we add the distance of the objects to the camera. So basically it's the depth. And it augments this and maintain the regular structure of the grid. And then it's natural to extend this to a voxel grid where you have the ambient space and you have the objects represented there as a function of the ambient space. So this is what we are going to see in the first part of the lecture. And then also notice that the fact that this is a regular representation and extends image, it means that we can exploit CNN architectures, convolutional neural networks, and use convolution as the operator for learning, analyzing, and doing both analysis and synthesis, classification, reconstruction, and things like that, and generation. So we're going to start discussing depth images and normal maps. So what is a depth map? A depth map is a 3D shaped representation that augments an image with the geometry from the point of view of the camera. So for each pixel, the depth map gives the distance of the object that is seen from a ray that emanates from that pixel from the camera. So basically, it's, in the coordinate system of the camera, we have the sample geometry information along the rays. And so in that sense, representation is a 2.5 because we have the screen, the image that's 2D, and we have the visual information with the radiance that comes from rays from the scene. But then you have associated with the depth of the object that is reflecting that illumination and transmitting that visual information to the camera, and is registering that point of the image. And notice that this type of data is very common because there are many devices that can directly capture this 2D and a half representation, depth images, like the Microsoft Kinect. Now, you know, the top of the line mobile devices, the iPhone, the iPad, and some other mobile devices, they have both RGB-D cameras and also LiDAR cameras that directly capture depth. And then this can be used for in many applications in the context of neural networks for representation, analysis, learning, and we are going to discuss the networks that implement that. And so here we see, you know, that map associated with the RGB image. So we have like here the color, and here for each point here, this pseudo color represents the encoding of the distance. So here, like you know, the red, yellow, they are far, and the blues are near. So you see, like in this corridor, like this is a far point, objects from the camera, and here, you know, the couch, and they are close to the camera. And so basically, what we can do from that is to reconstruct those surfaces from the point of view of the camera, and we can put the visual information there. So we have like a, you know, a textured geometry. So how do we implement a neural network to learn this and to predict that? Basically, what we are going to do is to supervised learning. So we have pairs of RGB and ground truth depth image. And then, because we have a regular structure, we can use a fully convolutional network to predict the depth image from this input image. And would be natural to think that what we have to do is just to compare the prediction with the ground truth using, for instance, a simple per pixel law. You know, the loss would be L2 distance between the prediction and the true value, and then train the convolutional neural network to predict this images for several images. And so the neural network will be able to extrapolate, and from a given image, give the depth, right? This would be the intuitive idea, but this has a problem. The problem is scale and depth ambiguity. We have seen before in the course that project transformation, what the camera does, the camera projects the 3D information onto the image using a projective transformation. And that projective transformation is defined up to a scale. That means that like an image of an object can be the same if we change the scale as the object was near or far from the image. Like this small object that's close to the camera is going to be projected over here. And if we take this object and change the scale and put it far, but with a larger scale, it's going to project exactly the same way. So that means that we have images that are in different distances because they are projected considering different scales. So the relative scales of the object within a scene is defined, but the absolute scale is not, because the project transformation is defined up to an arbitrary scaling. And so this is a problem that we have to solve if you want to design a neural network that's going to learn depth, right? And so the solution for this is actually to change our loss function. So instead of using a loss function that just compares the depth values, we need to design a different metric, a loss function that's going to be scaling invariant. And so this is what's done in this research. And what they did in this loss function is that they have this a function alpha that compares the depth predicted and the depth of the ground truth. And this is done globally. And then this alpha y star takes into account, all the points, and then and basically what it does is search for the value of alpha that minimizes the error for this set of values. And so when you predict, you try to learn a scale that best aligns with the ground truth globally. And so in that case, all the scalar multiples will have the same error, and then the scale will be like invariant. And so this, with this, we can really have here just replacing the L2 by this new loss. We can learn the depth that is scale invariant, and this was like a groundbreaking result that enables to predict the depth and have depth maps from images. So continue on. Also important problem, and actually easier problem, is to from an image compute the surface normals. And not that here we have a simpler problem because the scale is a global factor. And then we have to introduce this scale invariant metric and change our loss function. But for normals, we don't need to do that because normal is a local property of the surface. So we can do is if we have pairs of images and normals, or actually if we have normals and depth, the normal, if we integrate the depth images, then we get the gradient, and from the gradient we get the normal. And so we can train a neural network to predict the normals, and that normal is important because we can go from the normal to the geometry and have this as a useful representation. And so here we are showing the image, and then here that's not just a scalar value, that's the distance, the depth. Here what is encoded is a color coding of a unit normal. So we have like three components, x, y, z, and you can imagine that this is normalized, a unit vector, and this encoding basically reflects this, right? In fact, this normal map has three channels, right? And then the way to learn normal maps is similar to learn depth. So we have the RGB image, and then you have the ground truth normal. And here, our per pixel loss, what we're going to do is going to try to align the predicted normal vector from the network with the true normal vector. And basically to align means that they have to be parallel, have the same angle. And for that, we use this loss function. That's the dot product of the vectors in x and the vectors in y. And then we normalize this. And so this is because, the dot product is exactly the cosine of the angle between these two vectors. And we want this to be 0. And we want to minimize that. And this is very simple. and very effective, and sort of complements this 2.5D representation. So we have images with depth, and images with depth and normal. Okay, so now we finished this first part that we discussed the intermediate representation between image and 3D. And now we are going to full 3D, that's the volumetric data. And notice that volumetric data is very important in applications because it comes from many different areas. Like in medical images, we have sensors that collect like MRI, computer tomography, and to represent this using machine learning, both for analysis and synthesis, is very important. And the data here comes naturally in those volumetric 3D representation. Also in other areas, like in geology, for this types of applications, like a gas and oil, and you want to kind of understand, some oil fields and gas fields, you need full 3D information, and that you have sensors for that, and simulations that you need to run on this kind of data. And also in manufacturing, we need also to do analysis of shapes and different properties with finite element analysis in manufacturing. And there's also some simulations that comes from the manufactured data when you are designing and analyzing products that you need to build and know their physical properties. And even for simple objects that in computer aided design, in computer aided manufacturing, we can take the CAD models and create this volumetric representation. So this, it's natural to take 3D data from different areas and create this 3D volumetric representations. So what are the representations that we are going to use? Basically two kinds of representations. One that would be a natural extension of an image, that would be like a 3D grid. And so it would be the 3D counterpart of a 2D image. And then we are going to specialize that to make that representation sparse for several reasons that we're going to discuss further. So we are going to first discuss the 3D representations that are voxel grids, and then the sparse voxel representations. So starting with the voxel grid, what's a voxel grid? As I said, the voxel grid is a natural extension of an image, but the information that's contained in this grid, this if you have an image, it's an image that has 2 dimensions, 2 by horizontal and vertical. Now we put like a third dimensions, the depth, and then that's something that we did when we created the 2.5D, but now we have the space there for all the points, not just one point that would be the distance. It will be an attribute of the image. And then what are the information that we are going to put in this 3D grid? The information that we are going to put is the occupancy. And that's exactly what we are saying, that this is a extrinsic representation. It's a function of the ambient space and a function that tells the points that are occupied by the object. And there are the points that are not occupied. So it's an indicator function. And what are going to be in these elements that we are going to call voxels. Each element of the grid is a voxel. And the element is going to be 1 if it's occupied and 0 if it's not occupied. So conceptually, it's very simple, just a 3D grid with occupancy information. And this is the nice thing about this representation. But there is the downside. The downside is that because we are doing this discretization and we are changing from 2D to 3D, and we are augmenting the dimensionality of our domain, we are subjected to the curse of dimensionality. And then that means that we need to capture fine structures, a lot of fine resolution. So we need a grid with a high resolution. But scaling the representation to high resolution is not trivial. And so we are going to discuss all the properties of voxel grids, and then we are going, in the end, to analyze these downsides and see how we can deal with them using a smart data structure, taking into account the characteristics of the representation. Okay, so the general idea here is that because we have a regular structure that's just a 3D grid, it's simple to convert irregular representations like meshes and other representations that are in 3D to this regular 3D grid. And in that sense, we can circumvent artifacts and problems with this intrinsic 3D representations like meshes and point clouds, because we can deal with non-manifold geometry, polygon soups, just points. So to convert any 3D representation for a volumetric 3D grid is simple, and we are going to see how simple it is. And also it means that since it's a regular structure, we can extend the convolution operator to a 3D grid and take advantage of everything we know about a convolution neural network for images, and even use and combine this with 2D and 3D convolution neural networks. Okay, so the process to convert any 3D object to 3D grid, a volumetric 3D representation, is called voxelization, and that process follows this straightforward idea that we're going to extend the domain to the ambient space to 3D and consider that each point of the grid represents the occupancy of the voxel. And as we said, this allows us to use extend CNNs to 3D and design 3D convolution neural networks. So what's a convolution neural network? So is a 3D CNN that's going to operate on volumetric data. And so that means that we are going to extend the convolution operator from 2D to 3D. And basically, we are going to use 4D kernels. So we extend, like in this example, we have an input voxel grid, 30 by 30 by 30. And then here we have like 3 layers, okay, with in here we have just one information, that's the occupancy, and then we design, in that case, several filters, 48 filters that are 13 by 13 by 13, and then we apply this convolution operator and keep going, and then in the second stage we have this reduce it to 5 by 5 by 5 with 160 filters, and then in the end will be like a 2 by 2 by 2 features with 512 channels. And this is similar to what we have seen in 2D neural networks. The only difference is that we have this filtered kernels with higher dimensions, but the rest is the same, right? And so to do the convolution, we are going to process the voxels for analysis, like a classification task. We are going to do exactly what we have seen here. Like in this example, is the same of the previous slide. We start like with the occupancy and a resolution 30 by 30 by 30. And then here we use a 6 by 6 by 6 convolution and translate this into 48 channels with resolution 13 by 13 by 13, right? And keep going with a convolution that's 5 by 5 by 5, and then augment this with 160 channels. And finally, we have like a 4 by 4 by 4 convolution, and that with 512 2 by 2 by 2 features, channels, right? So for classification, in the end, we take this and have a fully connected layer that's going to analyze those features and give, for instance, classification scores. Notice that's the same process for an image, but we are not dealing with visual information of the image. We are dealing with true geometric information for the occupancy of the voxels, right? And we can also use the same process for synthesis. So in that case, we have to use not only convolution, but deconvolution. And we can, as I mentioned before, we can combine 2D convolution neural networks with 3D convolution neural networks and take advantage of your operating convolution in different domains and work with images and shapes. Like in this example, we have an input image and we have as a ground truth a voxel grid. And we want to learn how to generate this. And so what we can do is we have a sort of like an encoder and decoder that would be similar to a full convolution networks in 2D, but this is a mix because here we have, like in the first stage, we have a 2D CNN that's going to take the image and create 2D features. And then we are going to project this 2D features to 3D, putting one more dimension. And then we have like a 3D econvolution from this 3D feature vector to expand this and generate a geometry training on this ground truth voxel representation with cross-entropy laws. Right? So we can do a lot with volumetric representations and 3D CNNs. And this was a natural evolution of the area, but there are problems. So what are the problems? We have like three main sources of problems. One source of problem is an approximation issue. The other is the complexity issue. And finally, is memory usage. So the approximation issue means that when you have true continuous geometry or even approximated geometry for a 3D object, like the polygon mesh, when we do the discretization in an occupancy grid, the resolution of the occupancy grid is going to make an approximation of this true geometry and topology. And depending on the resolution of the grid, we have information loss. Information loss in terms of geometry and information loss in terms of topology, because notice like the handle of this teapot. If this was very small, smaller than the size of a voxel, we wouldn't be able to detect the handle, right? And so these kinds of things, I mean, like, have to be taken into account in consideration of the representation, because it's a discrete and approximate representation. Also, there's a question of a complexity issue that we need a neural network that is going to process using 3D convolution operators and represent features in 3D. So the network will have a number of parameters that will depend on the resolution, and the resolution is volumetric, is cubed, right? And then so here comparing AlexNet that was on the first 2D convolution networks that has a significant size for an input resolution of 224 by 224, it had like 5,000 parameters. And here this typical 3D convolutional neural networks with resolution 30 by 30 by 30. It has almost the same number of parameters with 10 times less resolution. So we go from 200 by 30, and here from 50 to 30, 50,000 to 30,000. And so it's easy to see that the complexity for even small resolutions is very high. And we have to deal with this, right? And finally, the consequence of this issue of resolution and dimensionality. Here is where the curse of dimensionality really shows, because the memory grows exponentially with a cube, right? And so here is a plot of the voxel memory usage with the resolution considering floating points to the memory for the information, right? And so to store a voxel grid that would be 10,004 cubed takes 4 gigabytes of memory just to store the grid. We're not considering the network and everything. And you see that it goes exponentially because this is a log scale, right? And so we have to deal with these 3 issues. And how is the solution to deal with these 3 issues? The solution is to search for sparse voxel representations. And to understand why this makes sense, we have to understand the nature of this volumetric representation. And so if we analyze the 3D volumetric representation using voxel grids, we are going to notice that there's a relation between resolution and sparsity that is in our favor. Because look at this, we are interested to represent the occupancy of functions in space. And as the resolution grows, the percentage of occupied cells gets smaller and smaller. So that means that there are many empty cells that they keep empty, and as we refine the resolution, we have less percent in terms of percentage, less occupied cells than empty cells. And so here we have like a 32 by the cubed in resolution, and then 10% of the cells are occupied. And here we have 64 cubed, and only 5% are occupied. And here we have 128 cubed, and only 2% are occupied. So basically, for each time we double the resolution, the occupancy is divided by 2. And so that means that this representation is sparse. And so how can we take advantage of that to create a representation that is going to compensate all those issues that we have seen that are related to resolution? The idea is to store only the occupied cells in the grid. And notice that what we are really interested in to design, define the surface that's actually 1 dimension less, 4 dimensions in this volumetric space. So here, like in this the bunny, we want to have a lot of detail with the surface of the bunny on the translation between the transition region that from inside to outside, right? And even if we need the information inside, then we can do that adaptively too. And so we replace the full voxel grid with this kind of representation that is going to concentrate on the occupied cells. And so the trick here is how to skip the empty cells that we are not interested interested in because there's no information valid for us. Here, we already see visually what is the solution. So notice that like in the parts that we have the occupancy, we have like a small cells, right? And in the dense 3D convolution network, all the cells are small, right? Because it's regular, we didn't do anything. But here we have like big cells for empty parts and small cells for the occupied parts. And so this gives an indication of what would be the natural data structure to use. And the natural data structure to use is the octree, because the octree recursively partition space subdividing the occupied cells. And so if I have this cell that's not occupied, I don't need to do anything. But then if the object is inside the cell, we subdivide it in 8. That's the name octree. And then for each children, we do the same. And then we keep only subdividing where we have the object for occupied cells. And the leaves of these trees that are occupied are the leaves, the cells that we are going to process. And this is a very common data structure in computer science. And we can adapt this data structure for neural networks and do machine learning for sparse volumetric representations, right? And so with this, we implement the octree-based convolutional neural network. So we have like some objects converts to a volumetric representation, creates an octree with this volumetric representation. And then we are going to do the same operations that we did for other convolutional neural networks, like for images or voxel grids with this octree. But we need to solve some implementation problems in terms of techniques in computer science, because we need to implement efficiently the convolution operator, and we need to, when we do other operations like pooling and other operations, we need to make this suitable to work with this hierarchical data structure, because the octree is a hierarchical data structure, right? And so the two issues that we are going to do is like one, use a hash table to index the neighborhood, because the convolution operator is operating one voxel and needs to take into account the neighboring voxels. And so if we have a hash table that works with the octree and are going to tell where those neighboring voxels are and whether they are empty or not, we can implement efficiently the convolution. And then because we are dividing each voxel to create the octree by half in the 3 dimensions, that's the way we create the 8 children from that voxel, we are going to use a stride of 2 that will be compatible to hierarchical structure of the octree. And so that enables to use this network. And so here's just an example what we do to do convolution of the octree. We are processing like the central element. This is our mask, and we need those neighbors. And for a full voxel, this just use the structure. But for an octree, when you have this neighborhood, we have the index of the neighborhood, I, J, K, and then we have a hash function that are going to give us the neighbors, and we can access this very efficiently, including using this, implement this in the GPU, right? This is something that is already well developed for games and other applications. And also, as I mentioned, the octree is a hierarchical data structure. And if we implement the change of resolution according to the structure of the octree, not only gives us the change of scale and change of resolution, but also gives a way to work with multi-resolutions and adapt the occupancy to different resolution levels. because we can start like with our op tree, and then we can take like levels with different resolutions and combine them and subdivide where the geometry is finer and leave other parts where the geometry is not so fine. And so in this car here, we have like 3 levels, 32, 64, and 128. And like some parts, they remain the same. They are not refined, and the other parts are refined. And that gives us more advantage in terms of representation because multi-resolution not only saves space, but saves computation. And so the idea here is to do this progressive voxel refinement. What it means that then we can consider that as we propagate features through the neural network with convolution operators, we are going to have consider not just occupancy, but partial occupancy. So we propagate a feature, and then as we propagate and you change the resolution, we have like empty cells, cells that are totally filled, and cells that are mixed, that's partially filled. And then we compare this with the ground truth, and then that will enable us to search for the right resolution level when we work, and also when we do the operations and classification, things like that, we can consider this into the implementation of our operators in the neural network. And here we see the results, where we can go up to 256 cubed with very good resolution, comparing to a ground truth with the 206 cube. And you see that here we have a very good approximation and is adaptive, right? And this is in the state of the art in 2017, right? So nowadays you can go even further because of the improvement in terms of the devices, computation, and technology. And here we can see clearly the advantage between a voxel CNN and an octree CNN. You see that like for voxel CNN, we can go up to 64 cubed, and then it becomes unfeasible, not practical to do it. And then for octree CNN, we can go beyond 256, and we still can do it very nicely. And so that's the state of the art for volumetric representations using 3D grids around 2017, 2018. Okay. And now let's see what kind of applications are enabled with these voxel CNNs. We are going to see 2 types of applications. One be like a 3D classification, and the other 3D reconstruction. So the 3D classification is actually very trivial because, as I showed, it's just extension of 2D to 3D. Instead of considering the visual attributes of an image, we are going to consider the geometric attributes of occupancy, right? And like in 2017, actually even earlier, in 2015, we have the first 3D CNNs to do classifications. Like these are 2 examples, this one from Princeton, and then this one from Carnegie Mellon University. And they got for classification of 3D shapes results that were like around 80% of achievement, right? And if you compare this with multi-view 2D CNNs that were very well developed at the time and used images, what they had was like results that are around that. Here's 82% times 90%. So the first 3D CNNs for classifications were on par with the multi-views 2D CNNs. And so that means that it was a successful application, and also means that this type of application for analysis, we can combine 2D and 3D as we saw before, and we are going to see next, in many different ways, and take advantage of combining 2D and 3D CNNs. So now let's go to 3D reconstruction for multi-view, because here we had like a pure 3D classification, and here multi-view classification. So why not combine these two things for reconstruction? And this work is an example of that. This work actually uses a 3D reconstruction for multi-view images using a recurrent 3D CNN. And just as a remark, in the course, I didn't explain exactly what is a recurrent CNN. I just gave the basic architecture. And this was a result that used a recurrent network that has convolutions. And so there are two advances in this result. And this is very clever, because what happens that it processes different images from different points of view. And so we have an input view image, and we have the ground truth voxel occupancy map. And we have like this recurrent 3D network that as you give more views, it's going to learn more from the object. Because if you give one image just for the front of the object, the image just represents the front of the object, but the ground truth occupancy gives the full object. And then if you give other views, it's going to correlate those, combining what's in the image and what's in the 3D space for the occupancy. And it's going to refine the geometry the more views you give. So if you give just one image, it's going to give a good result, but from that point of view. But if you put more views, then you are going to refine, taking advantage of this recurrent 3D network, because it's going to train the same network. In this example, here's actually only one network that's going to be trained, like continuously for each, view, right? And so let's see more in detail how that's done. So the structure of this recurrent 3D network is like actually I encoded the decoder to be like generative, right? So the first part, the encoder, is a 2D convolutional neural network. And that 2D convolutional network is going to produce a feature, as we have seen before, right? That is going to be passed to this 3D convolutional LSTM, that's a recurrent network. And then like the features are going to be assigned to different nodes in this 3D LSTM. And here we are going to combine convolution with the recurrent neural network. And then the final, the decoder, will be a 3D deconvolutional neural network. So here is in 2D, here is in 3D, and here is in 2D with a recurrent structure. And then with that, we get all the results we want. And what this was done was supervised learning with ground truth, with the images and the occupants volumes, and was trained on the shape net, because it was easy to do, because we had the shape nets of different shapes, a big database, and they had like a 50,000 CAD models. And so they render the CAD models from arbitrary views. They shows the number of images in random order. It had a random background, and then they trained and made experiments with different number of images. So here's the result. You see that like when you have just one view, the result is not so good. It's reasonable, but basically from the back you see very well, but from the front you didn't see the front. What can give you is like that, right? But then as you give the sides and things like that, you get a very nice representation of the 3D shape, and then that can be extrapolated, and then you can see the views, you can get those results, right? And they use different objects in the shape net. This is basically shares and tables and things like that. And you notice that it can kind of represent like thin structures, different topology, and works like very well. Okay, so now I'm going to give a pause for us to have the question and answer. Okay, so continuing, we are going to discuss now in the second part of the lecture deep implicit models. And as I mentioned, in this lecture, we are discussing extrinsic 3D representations. And in the first part, we discussed volumetric grids. That's a discrete extrinsic 3D representation. And now we are going to discuss deep implicit models. That's a continuous extrinsic representation. And historically, this was a sort of like a continuation of the search for different architectures for AI graphics and 3D models and 3D scenes. And so what you are going to see in the second part of the lecture is, first, we are going to discuss some basic concepts about implicit representations and implicit functions. Then we're going to discuss implicit surfaces in practice, how we use them, and how to take these concepts and the practice of implicit surfaces and put into deep neural networks. It will be like deep implicit surfaces. And then I'm going to give a historical perspective of how that's all started. That was the deep implicit revolution. And I'm going to talk about the first and second generation implicit neural networks. So starting with the basic concepts, let's understand what the implicit function is. So the implicit functions for our representation of 3D shapes is a extrinsic function of the ambient space Rn that has values in R. And in that sense, this function is a point membership classification function because it classifies points of the space. And it can, and in terms of by construction, we are dealing with shapes that are regions of the space. So shapes that divide the space in two parts, the inside and outside part. And this point membership classification function is going to tell us which points are inside the shape and which points are outside the shape. But this function is very powerful because it can represent both surfaces and volumes. If we see the function in itself, we are basically saying that as we evaluate the function f at the point x, if the value is less than c, it's an arbitrary level, is inside the shape, and is greater than c, is outside the shape. And notice that this c is just a notation, because if I change c for the other side, I can normalize and say less than 0 or greater than 0, because f of x minus c would be the same comparing to 0 as comparing to C when the C is on the other side, right? And then, I mean, if we want this to represent the volume, this can be represent indicator function or any other function that are going to obey this point classification memberships function. And the usual ones are indicator functions that it has a 0 or 1, right? And you take like an epsilon that will be, you know, the transition between 0 and 1, right? Or you can take, you know, a sign distance function that's a scalar that it's related to the distance to the surface. We are going to discuss these two types of functions here. But in general, any classification that classifies a point inside and outside is good to represent volumes, solid shapes. And this is important in terms of physics because in the real world, all the objects are solid, right? Even a sheet of paper is solid, very thin but solid. But for some certain processes, we want to consider just the surface. And the surface is what we call a level set, because when you introduce this idea of level sets, I was saying that this C is an arbitrary level, and but if I change the C, I'm going to have different levels, right? And if we say like inside or outside, we are not discriminate other levels, but depending on we get the C, we have like parallel surfaces with like a C, C plus epsilon, and etc. Right? And in this case of a surface, the surface of interest would be the points which this function takes the value C, right? And what that would be in terms of a description would be actually the inverse image of this value C, right? And so a level set it would be like F inverse F minus 1 of C. It's a set of all points for which F of X takes the value C. Okay, and here we see like graphically, like the points that are in this level set, they sort of divide the space in two parts. And here we took C as 0, and so the points where this F is 0, there's this surface. And then when F is greater than 0, is inside the surface, and less than 0 outside the surface. And here we see like this bunny image with a sign distance function. You can see all the parallel surfaces for which the distance for the surface gets larger and larger. So obviously, when the distance of the surface is 0, is the surface itself, and is this F minus 1 of C. Okay, and so it's very powerful, a very powerful string representation. And how do you put this into machine learning and neural networks? We have like neural implicit models. So the model of that function is going to be a neural network with parameter theta. And then there's a function of that to be represented as a coordinate-based neural network, and the values of that we are going to train the network will be the parameters of this function, the parameters theta, and we are going to train this with samples from the actual function, and this is going to model a function that's a continuous function of space, can be evaluated in any point of space. This X takes in value continuously in space, and is going to classify points, and is going to define surfaces. And so to create this neural network, we have data samples that are going to have values greater or less than 0 or 0. And then we are going to train and create a model, and the model be this neural network itself. And then as the network is trained, we can use that for inference. And then the trained network with give points, and then we're going to give values, and it's going to be like operating with this continuous function as any other implicit function. And there are many uses for that, because we can use for surface extraction, for rendering, for different types of analysis. And for applications, we basically combine data with the model into some application, and we are going to have as a result geometry, images, and other properties. Okay, so this is the scenario of neural network modeling. And so how do we implement that? We have to go from data to models. And essentially what we are doing, we want this neural network to represent a function. So in that sense, we are doing regression with 3D supervision. So we want to fit these neural networks, f of x with parameter theta, to some data sets xi that are the coordinates of points with the corresponding values, right? So to train, we have the data points, and then we have a loss function that are going to align and train the network to predict the right value of this ground truth function that's evident by the samples, because the samples are pairs of coordinate and value. And this regression, we want a continuous function that generalizes and gets the right values in the sample points, and in all the other points, they are going to generalize well in the sense of that are going to have the properties that we want. And for inference, we just input the coordinates, and then we have the function value that's going to be working for this function. Notice that here, I'm assuming that the data are coordinates and 3D geometry. But we can use this in the context of multi-view. We can use differentiable rendering to learn this model from images. In that case, we need, as we have seen previously in the class, the images with the corresponding cameras to generate rays, and from the rays, train correctly this neural network. Okay, but here I'm saying I give this coordinates, and I'm just assuming that the coordinate is from one object, right? But we are training a neural network, and so we can not just learn one shape, but learn a family of shapes. And so to do that, we extend the training to several shapes. And so we have a shape space, and then this parameter theta, we're going to index by this index I. And so in the shape space, we have many shapes, and each set of parameters, theta I, is going to be one surface. And in that sense, we have a generalization of shapes, and we are parameterizing the space of shapes, and learn this from data from different surfaces with different properties. And there are two basic methods to do that. One using conditional learning, and the other uses meta-learning. Here in the course, I'm going to discuss this conditional learning, and I'm going to talk about the autodecoder. But there are others that use meta-learning that use hypernetworks. The difference that the condition learns the latent embeddings directly. And then the meta-learning is learning the models for latent codes in a meta-learning fashion. Like, for when you do initialization, and you do like a meta-initialization to retrain a neural network, the hypernetwork is in that sense. And the autodecoder is more direct, and I'm going to give examples further on in the in the lecture. Okay, now let's discuss implicit surface in practice, because we see the big context, the concepts in theory, now have seen how things work in practice. As we discussed, the implicit function, the point classification, and the neural network, they are all based on coordinates. A coordinate neural network that is trained using data samples. You have the coordinate and the value. And so to work with implicit functions, we need to sample this function. So we give point samples for which they are in the surface. So the value of f is 0. So I give all this. If you imagine, for instance, you have like a curve or a mesh, so you have the vertices. This would be the vertices of your geometry, of the surface that you are interested in. And then we are assuming that there's an inside and outside. So, but first you give this point sample with f equals 0. And then you have to define a function that has the value greater than 0 outside, smaller than 0 outside, and greater than 0 inside. And so for that, you can give other values, and these values depending on the kind of function you need. If you want to train an indicator function, we can give a value that's arbitrary. It just have to be greater or less than 0. But if you are training a sign distance function, you have to give the true distance. And then we are going to see examples of both further on in the lecture. And so you define that function based on the other values. Here you see plus and minus. And then as we define this function, you can extract this 0 level set. That's the surface at our interest. So you see here that the implicit function kind of generalized and it's very smoothly follow the contour, right? And we only gave those points and those very sparse points, and you get like this continuous representation, right? This continuous representation. And if you want to convert this to a mesh, recall a volumetric data structure. We put in a volumetric data structure and consider that the surface basically divide the space into cells, can be like cubic cells. And if the vertices of this cell have different signs, less or greater than 0, considering the surface at the level 0, it means that the surface passes inside that cell. So that cell is partially occupied by the volume, right? And so using this, we can use an algorithm that's very popular in graphics. That's the Martian cubes algorithm. So we divide the space, and dividing space, we evaluate the function, the vertices of this subdivision, and then noticing that if the signs of the values of the vertices are different, means that the surface is inside that cell. And so that's the Martian cubes. And the Martian cubes, based on those signs, decide what to do to create a polygon, or one or more polygons. And remarkably, there are only 15 cases if you consider symmetries and etc. Like in this first case, all the signs are the same, is either inside or outside. But here, this sign is different than that, the other ones. So it means that the surface passes here and has to cut these 3 edges, and you put a triangle here. And so on. I mean, like these 2 are inside, the others are outside. Then you put like a quadrilateral or 2 triangles and things like this. And then, so it's very easy to do and very fast to do, because basically you classify the vertices, identify the cases, and have a template, and put the. And notice that here we do a piecewise linear approximation of the mesh, because if we have, for instance, sine distance function, we know the distance to the surface. And so we know the distance to the place where the level set 0 crosses an edge. And then it's exact where, but we approximate with polygons, and then we apply piecewise linear approximation. And there are ways to smooth that and everything. And then if you want to render implicit surface, we do ray tracing. Why? Because we have this function, S of xy equals 0. That's the implicit function that defines the surface, the level set. But to do ray tracing, we have a ray that's parameterizing. You have the origin of the ray, the direction of the ray. So the ray is defined as O plus T of D. O is the origin and D is the direction. And for this parameter T are points along the ray. So we want to, when you do ray tracing, to identify the point where the ray intersects the shape, intersects this surface S of xy equals 0. And it's very easy to do. You just replace O and D with X, Y, and T. And then you want to search for the points where this expression is 0. So this will have like a polynomial, and we are going to look for the roots of this polynomial if this function is algebraic function. In the case of a neural network, we do the same, evaluating the neural network. And so it's very natural to do ray tracing with this surface. And furthermore, when you find this T0 is the intersection point, we compute the normal and then do shading and do other things, right? So it's natural to use this function for rendering also. And so here we can use, as I mentioned previously, we can use for surface extraction using Martian cubes and rendering using ray tracing. And there are many other things we can do with this representation. Okay, now what I'd like to do is talk about the use of implicit representations for neural networks to be like the deep implicit surfaces. And conceptually, we have all these concepts in machinery, but we have to put a neural network to work with them. And there are two things we can learn, either an indicator function or a sine distance function. So I'll start discussing, learn the indicator function, and then in the last part, I'm going to discuss how to learn a sine distance function. And so if we consider the indicator function, what we want to learn is a decision boundary, because that surface is decision boundary that separates the points that are inside from the points that are outside. And the network takes as input, it's a coordinate-based neural network, takes input the samples that are points, the coordinate of the point, and the value of the point. And from that, it has to train that function. So this network is going to predict the point occupancy, like we saw in the volumetric representation of volume grids. So, but in a continuous sense. And that's going to do the same way supervised training using the ground truth occupancy. And the ground truth occupancy will be like these samples. And we can use multi-resolution for surface extraction because we can apply the Martian cubes algorithm in multi-resolution. And that is more or less the same spirit of the op trees, right? But in that sense, for surface extraction. And the implicit representation as a neural network are going to compute this decision boundary using a neural network. Also, in that sense, is implicit because does not represent the shape explicitly. Represents the shape implicitly through this classification function. And we consider the surface as a decision boundary in the case of the neural network of a nonlinear classifier, because it's a point membership classification function. The neural network knows how to do classification and is going to do a nonlinear classifier. And so what we want to do is like give points that are inside, give points that are outside, and it's going to learn a classifier that's going to distinguish inside from outside. And the neural network itself is going to be an indicator function because it's going to give a 0 if it's occupied, and occupied, and 1 if it's occupied. And the input is a 3D location. But if you want to learn a shape family, we can put a condition. So the input here is going to be a 3D location plus a condition. And that condition can be a latent code, can be an image, and then that's going to indicate which shape we are going to talking about. And here we have an example. This is a 2D example, is a linear classifier separating red to blue points. But here is a true example of points that are outside this couch, and the red points are inside the couch. And it's a nonlinear classifier that classifies and generates the surface of the couch, extracting, for example, using Martian cubes or ray tracing. And if we train with many shapes as a condition, we can use for generation and for shape interpolation, because we have a latent code that's corresponds to one of the shapes, and then you select the parameters using this latent code. And if we interpolate the latent code, you can interpolate between nearby shapes. And then we can morph between different types of couches, different types of cars, and everything. Okay? So what are the advantages of this representation? The first main advantage is that the continuous representation, there's no discretization. The second is that it doesn't have any problems for resolution because it's continuous and can represent shapes with arbitrary topology. You can change the topology very nicely. That's something that other intrinsic representations don't have, like a mesh. To change the topology of a mesh, you have to do some surgery to cut and holes and things like that. Here, it's very natural to change the topology. You have to follow total control. And it's very compact. It's very low memory footprint, in spite of the fact that it's a continuous representation. And it's also not restricted to a specific class of objects. It can deal with any kind of object and with shape families, right? Okay, with all these advantages, it's not surprising that the researchers try to do this in practice for neural networks. And then comes the deep implicit revolution that was the point to have the community of researchers design the first implicit neural networks and show the results. And so trying to give a historical perspective, historical evolution of this is in 2019, in the same conference, 4 papers appeared, CVPR, all dealing with the first generation models of neural implicit surfaces. And they are variants, but they're basically on the same idea that I'm going to describe next. And then from that on, 2020, 2021, 2022, further generations, second generation models, third generation models, fourth generation models, and the thing keeps evolving. So this is the state of the art in machine learning. And in the final part of the lecture, I'm going to describe these first generation models, and I'm going to describe these 4 models that are very similar, so you can understand what are the similarities and differences between them. And they are all to compute indicator functions. And then I'm going to describe this this siren model that is a sign distance function that's representative of this implicit neural fields using sign distance functions. Okay, so starting with the first generation models, these 4 papers from 2019 that represent the CVPR, they introduced that to the community. And so the first one is this occupancy networks. There's also the one learning implicit fields with generative shape modeling, deep SDF, and deep level sets. So I'm going to discuss each of them in turn. Starting with occupancy network, the architecture of the occupancy network is like this. Is a task encoder and a sequence of ResNet blocks. And here, this task encoder is going to do some conditioning. And this second part is what is trained for the model. And then what does is like you can condition on an image, condition on points, or condition on a mesh. And here you have an encoder that knows how to, from image or points or mesh, get this a code that is going to condition the network. And then based on that, we also need to have the samples for the geometry that's represented here. So we have sample values that are the coordinate x, y, z, and the values of the implicit function. And then it's trained using this conditional model with this combinator here that take the code and this is insert into this. This is a fully connected network. It's not a convolutional network, it's a fully connected network using a ResNet type of skip connection. And in that architecture, it has like 5 blocks like that. And what they do, they have like batches of size t with the coordinates. And then here we have the code. And then here it goes to this, layers with 256 layers here until the end, right? And this is the architecture of the second paper, the learning implicit fields. It's very similar because it also has an encoder, but it's a different type of encoder, and the architecture of the hit is a little bit different. So I have an encoder that you either start with an image or a point set, and here to create a feature vector, if an image you use a CNN, if it's a point net, you use for a point you use a point net and creates this feature vector that's size 128. And then you put the coordinates and the value, and then you concatenate, and then you have a fully connected network with a sequence of layers starts with 2048, 1024, 512, 256, 128, and then finally the final layer is going to give the value, right? And uses like a leaky ReLU and a sigmoids to do this. It's fully connected. And here you see a comparison between occupancy network and learning implicit fields. Here there are shape families for the implicit field learning. And here these are shapes from the occupancy network. And here is a comparison with other networks. And notice that this 3D R2N2 is the paper that we discussed when you're talking about volumetric representation. So here we have a direct connection and comparison between those two. And these other in the middle, they are like a pix to mesh that we're going to discuss in the next class. And this are the one that's a point net that we are going to discuss in the next class. Okay. All right. So, and then we have like the deep SDF. The deep SDF introduced one interesting thing. That's the reason I singled it out here, because if you see these two networks, they have a sort of like an encoder decoder, right? And the DPFDF, they introduced what they called autodecoder. In that sense, they sort of like divide the architecture in two types. If you want to train just a single shape, we have a network that enters the coordinates and the value and computes a regular SDF, right? But then if you want to train a family of shapes, you have this coded shape, a DPFDF, that uses the concept of autodecoder. So what's autodecoder? Autodecoder is going to learn a shape family through a latent code vector. But the idea is that the autodecoder trains the code itself. It's not computed by an encoder. And so what it does is like you have your shape, the coordinates and everything, and then you do a random initialization on this latent code. It's just random. And then as you train, you optimize the shape, but also you optimize the code using backpropagation. Basically, when you train and do backpropagation, you backpropagate the gradients to the latent codes. And in the end, you have the trained shape and the trained code. Okay, and then you can use that because you can have like a library of primitives, and then you give that and you do for your network, and then just generate that. But this is interesting because allows some kind of other operations, because you can, after training for a shape family, you can do operations like interpolation. We can do operations like shape completion. And then, for instance, for shape completion, what you can do, you have like some points of the shape, but not all of them. And then in the first part, the network was already trained, right? So you did this, weights of the network are frozen because the network was trained. But you can, in the first phase, learn the code by backpropagation based only on those samples. And then after you do that, you do shape completion because you have a network that knows the other side that was not given, and things like that. So that's what's something very ingenious of this autodecoder, and has many applications. Okay, and here are some examples of the DPSDF. So this is a shape family that they learned from this. It's a family of tables, and train in all of them, and then there are different ones. But you can also do like interpolation. So here we are doing interpolation from just interpolating the latent code from that shape to that. Interpolates very naturally, and you see that like the arms of the share are changing gradually, and the back of the share is changing gradually, and everything, right? Very natural, and that means that the probability distribution of the shapes has an embedding that makes sense for this kind of semantics. Understands the semantics correspondence between things. The same for cars. Or probably here they train it just for class of shares, and here they train just for the class of cars, right? So these are interesting applications of this out to the code. Okay, now to finish off, we are going to give an example of the next generation of implicit neural networks, and we're going to talk about Siren. Siren is a new kind of neural network, and this acronym Siren is the acronym for sinusoidal representation networks. What's the difference here? Because we have seen the activation function of all neural networks that we have seen, fully connected neural networks, convolutional networks. The activation function is one type of function that's not periodic. It's either ReLU or sigmoid or something like that, right? So Siren has an activation function, a sinusoidal function, a sine function. And this has two main implications. The first implication is that the fact that is a periodic nonlinear function, it gives us some shifting variance in terms of the behavior of the network. And the second, because it's a sinusoidal function, we are working in a spectral domain. In the course, we talked about like Fourier theory and everything. Here, the network is learning in the spectral domain. And not only that, in terms of differentiability and smoothness, is the best we can get, because it's like a infinitely differentiable, the network itself, because a composition of signs. And not only that, the derivative of the sign is a sign, it's cosine, and then there's a shifted sign. So the derivative of the network is the network. So these are two very nice properties that we can exploit, right? And in that paper, sinusoidal representation networks, the author, he puts this in a very general context for implicit neural representation, not just for shapes, but any kind of signal. Because any kind of signal that's a field, you can represent to implicit representation. And so the way he generalizes like this, you have like this functional that has to evaluate to 0, that considers the coordinates, coordinate points, and a network that's a network phi that basically is going to evaluate the coordinate. And then as conditions, we can put the network itself and the gradient and the derivative and of various orders, the gradient and continue on raising the order. And this takes into account the fact that the derivative of the network is the network itself, and it's continuously differentiable. And so the other ingredients here are constraints, because this functional has to evaluate to 0, and then evaluate to 0 means to have satisfy some constraints. And those constraints are based on the data and the properties of the neural networks. And these properties are expressed to these constraint functions. And then how do you train? You have a loss that is the sum of all the constraints based on this very general things, right? And the problem here is to find neural networks phi of x subject to that, all the constraints to be 0 for all the points in the domain sigma m. Okay, this is a very general mathematical formulation for the implicit neural representation. But here, what we want is to specialize to sign distance functions. And we are going to consider in this context how we use this to implement sign distance function implicit using this network. And so we have taken to that, we are going to consider that the input will be spatial coordinates, these 3D points. The output is going to be supervised by the value of the function, will be the sign distance. And here, this to be subject to the fact that we want to have a sign is going to be strange related to iconal equation. And so, so our loss is this iconal equation loss that has 3 terms. The first term is 1. That means that the gradient should be 1, because the gradient of a sign distance function is 1, because it's basically the distance, right? And then for points that are on the surface, it should evaluate to 0. And for those points, we want to align, because a sign distance function, we want to analyze the gradient of the network with the normal of the surface there. right? So these are these two terms in the number two. And finally, we want to penalize points that are off the surface to have a value that is different than 0. And so this first term is for all the points that are not on the set omega 0, they are going to be subject to this expression that's going to penalize those points. Okay, and so here we're considering the first term all the domain, the second term just the surface, and the third term the complement of the surface, right? And these are the results. Here we have like this tie starter that's a very detailed geometric model and has 10 million points. And the network that represents this is a 5-layer fully connected neural network with sign activations with just 256 units per layer, and gives this geometric quality. And trains very fast. Trains using Adam for 50,000 iterations, and you see the convergence. There's a very good convergence. And not only that, here is because the conversion is very fast, after just 5,000 iterations, you have already like a very good results, and it is like was a breakthrough when they showed this, right? Okay, so now I'm going to stop for final questions.